Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us here today in the third of our lessons on pre-algebra. Pre-algebra, we're excited to be bringing pre-algebra to you this year. We got about 80% of the algebra course done last year for my students, and now I'm doing this for my students. Hopefully you'll get some value out of it as well. We're talking today about giving rational numbers in decimal form. Our first two videos looked a great deal at the different numbers and number systems that we operate in. We're going to focus here for a couple lessons specifically on rational numbers and talk about how we work with those and manage those and change them from one form to the other in order to make it more convenient when solving problems. Now, just to remind you, a rational number is any number that can be expressed as a simple fraction. Any number that can be expressed as a simple fraction. If it can be written as a simple fraction, we call it rational. If we can't, we call it irrational. And there are a lot of things that can be written as simple fractions. Obviously, positive and negative fractions would be rational based on this definition. So if I have 1/5, that would be rational. 2/7, negative 13/4, or even something weird like negative 1013 over 5047. It really doesn't matter. If it has a simple numerator and a simple denominator, we would call it a rational number. But it is important to remember that all integers are also rational numbers. Because if I have an integer like a 4, I can write it as the fraction 4 over 1, or even as the fraction 8 over 2. Now the focus of this lesson is not about how to write fractions or change the form of fractions. Hopefully you already know how to do that. Otherwise you need to take a look at a different lesson. But it suffices to say that they can be written that way. If I have a negative integer like -5, I could do the same thing, -5 over 1. It doesn't matter if I put the negative sign on top or on bottom or even off to the side, it all has the same value. And even the integer 0 can be written as a fraction because it could be 0 over 1. All mixed numbers are fractions, or are rational numbers. So for example, 4 1/5 is rational because I can convert this to the form 21 over 5. Remember, this is not the focus of our lesson, is how to do this. That's simply just to realize that it would be rational. 17 3/8 would be 139 over 8. And negative 9 1/2 would be negative 19 1/2. Again, because I can write it with a numerator and a denominator, I would say it's rational. All decimals that terminate are rational. For example, 0.8, because if I read this the right way, this would be 8/10. 8/10 is a fraction, and of course it simplifies to 4/5. 0.72 is 72/100ths, which can be put as 18/25. Or even something like 124, if I read it the right way, would be 124,000ths, which would simplify to 31 over 250. Every terminating decimal can be written in fraction form. Here's the one where people have the most trouble. When I teach this in my class, I actually have them go through and either highlight this or underline this or circle this or do something to draw their attention. So when they're preparing for tests and quizzes, this is the one we really need to focus on not forgetting. And that is all repeating decimals are rational numbers. For example, 0.3 repeating, and I think I forgot to put my repeating symbol on here. 0.3 repeating is 1/3. 0.45 repeating is 5/11ths. And 0.15 repeating is 5 over 333. Now, in a later lesson, we'll talk about how to do those conversions, but for the moment, suffice it to say that if you have a repeating decimal, it would be rational because it can be written as a fraction. Now, here's what we want to do today. We want to be able to convert from different forms of rational numbers. Specifically today, how do we go from a fraction form of a rational number to a decimal form of a rational number? And we're just going to do that with simple division. Remember, if you have a fraction like 7/8, this is 7 parts out of the 8 needed to make a whole. Or if you look at this symbol, you can think of this as a 7 divided by an 8. That's really what that fraction symbol in the middle means. 7 divided by 8. Well, that's just a simple division problem. Remember, the numerator or top number always goes on the inside, the denominator or bottom number goes on the outside, and then we're going to go through and do some long division. I am going to spend a little bit of time doing the long division because I know that with people using calculators as much as they do now, many people have forgotten how to do long division or forgotten the process. So I'm just going to talk you through it very quickly. Again, it's not the focus of this lesson, but it is an important part of this lesson. So we'll spend a little bit of time on it. We're not going to go into too great a detail as to the whys of how this works. That's a lesson for a different day. Instead, I'm just going to ask myself, how many times can 8 go into a 7? Well, 8 can't go into 7 because 8 is bigger than 7 is. Therefore, I'm going to say it goes in 0 times. Now, I'm going to go ahead and add a decimal here because the 7 is in the units place of a number, which means it's going to be just to the left of the decimal. And I'm going to go ahead and stick a 0 in the tenths place. This is 7 and 0 tenths. I can add a 0 anytime I want because adding 0 doesn't do anything to a problem. That's the identity property of addition. 8 goes into 70 how many times? Well, let's see. If I know my multiplication tables, 8 times 4 is 32, 8 times 5 is 40. I can keep doing multiplication tables all the way up until I get to 8 times 8 because I know that's going to equal 64. If I take 8 tenths times 8, I'm going to get 6.4. 6.4. And when I subtract that, I'm going to have a remainder of 6. So 8 goes into 70 8 times with 6 left over. Now, when I get that 6 left over, I don't want to keep a remainder. I'm going to keep doing division until the remainder becomes a 0 or until I notice some kind of a pattern that I can represent another way. So I'm going to stick in a 0. I've just added on 0 hundredths. Adding on 0 hundredths doesn't do anything. That's the identity property. I bring my 0 down. 8 goes into 60 how many times? Well, 8 times 8 was 64, which is just slightly larger than 60. I'm going to try 8 times 7. 8 times 7 is 56, with a remainder of 4. Again, I don't want a remainder, so I'm going to keep adding zeros and bringing them down until it either goes away and gives us a remainder of 0, or until I notice some kind of a repeating pattern. 8 goes into 40. Oh, that's an easy one. 5 times 8 is 40, leaving me with 0 left over. Once I get 0 left over, I know that 8 goes into 7 this many times exactly. That's 875 thousandths. And there's your solution. And that really is all there is to it, as long as your decimal is terminating, or meaning it stops. Terminating says if you divide, it will go evenly, and eventually you will end up with a 0. Now, sometimes it takes longer than others, but it will always, always, always give you a remainder of 0 or end up in some kind of a repeating pattern. If you're pretty confident with this, I would recommend that you go ahead and try and do 3/16 on your own. Just pause the video, and then when you finish, restart it to see if you've done it correctly. I'm going to go ahead and keep doing this for those that are still a little bit confused. Notice 3/16 means the same as 3 divided by 16. Numerator on the inside, denominator on the outside. 16 goes into 3 0 times. So I'm going to add a decimal. Put an extra 0 in. I actually went one click too far. 16 goes into 30 one time, which is 16, leaving me with 14. Notice my remainder is not 0, and it did not repeat, so I need to do this again. Stick on another 0. How many times will 16 go into 140? That's a pretty big number, so I'm going to use a little logic. I know 10 times 16 would be 160. 9 times 16 would be 16 less than that, so about 144. This is probably going to be an 8. 8 times 16 is 128. I subtract that, I still have 12. As long as I'm getting remainders, I'm going to keep adding zeros, and I'm going to keep right on going until it stops or until it repeats. 16 goes into 120. Well, 8 gave me 128, so I'm going to use a 7 this time. 7 times 16 is 112, leaving me with 8. As long as there's a remainder, I'm going to keep adding on more zeros. 16 goes into 80, 5 times. 5 times 16 makes 80, and look, my remainder is 0. Notice I had to go out more decimal places than previously, but it did eventually terminate. 3/16 is 0.1875. Not bad, right? Again, if you're feeling confident, go ahead and give this one a try on your own. Let me point out to you a couple things. I'm not overly concerned about this -2 here. I'm really only concerning myself with the 3/5 because I already know my answer is going to be -2 point whatever this is. So as I'm working through the problem, I'm just kind of ignoring that -2 until the very end. I'm only concerned with the 3/5. There again, I would pause this if I were you, try it on my own, and then restart the video when you're ready. I'm going to keep right on going. 5 does not go into 3. So I put my decimals. Put in a 0. 5 goes into 30 6 times with a remainder of 0. I love it when that happens. One decimal place goes in perfectly and I am finished. So my answer then is going to be 2.6. Notice my negative sign is missing, so I'm going to have to write that right in there. Don't forget when you finish the problem to go back and stick that -2 back onto the front. It's not bad, right? Tell you what, let's look at something slightly different. I'm going to give you another example. This one is 4/9. We're going to start off the same way with 4 divided by 9, but this one's going to work out slightly differently. 9 still won't go into 4, so I add my decimal. And I'm still going to stick in a 0, just like I did before, and try and do 9 goes into 40. Well, let's see, 9, 18, 27, 36, 45. This is only going to go in 4 times. But notice what happens when I get my remainder. My remainders is the exact same number I started with. It's a 4. That's weird. Let's try this again. 9 goes into 40 how many times? Well, it goes in 4 times. I subtract that, I get a remainder of 4. Wait a minute. It's doing the same thing over and over again. No matter how many times I try and see how many times 9 will go in, I'm always getting a -36, and I'm always ending up back in a remainder of 4. Take a look. If I do it again, put in my zeros. How many times will 9 go into 40? 4 times. That's 36. Remainder 4. No matter how often I do this, this 0.4 is going to repeat over and over and over again forever. This is an example of a repeating decimal. 4/9 is a fraction that can be written as the decimal 0.4 repeating. Notice the little repeating bar at the top. That tells people that this is just going to go on and on forever without ever ending. Okay? You want to keep an eye out for those patterns. Terminating decimals are really easy to work with. Repeating decimals will require you to pay a little closer attention. Here's another one. If you feel pretty confident, maybe pause and try on your own. I'm going to keep going for the sake of everybody else. 12 goes into 5 0 times. Bring in my decimal. 12 goes into 50 4 times. That's a 48 with a remainder of 2. Notice this time it didn't repeat. Let's see what happens. I put in another 0. I have 20. How many times will 12 go into 20? Once with a remainder of 8. Still no repeats. I'm going to add another 0, bring it down. 12 goes into 80 how many times? How about 6? 6 times 12 is 72 with a remainder of 8. Hey, wait a second. I had an 8 here. I have an 8 here. Let's try one more. Put in another 0. 12 goes into 80 how many times? 6. With a remainder of 8. You see, I've reached a point where it wasn't repeating, but now it is. I'm going to keep getting 80 minus 72, 80 minus 72, 80 minus 72 forever. Up here, it's always going to be 6 times 12 is 72. So the 0.41 is not going to repeat, but the 6 is going to keep repeating. I'm going to write that this way. 5/12 equals 0.416. But I'm only putting a repeating bar above the 6 because only the 6 goes on and on forever and ever. Notice over here, I have only a repeating number. Down here, I have a portion that does not repeat that ends up in a repeating pattern. Let's try this one, 25 over 99. Again, this one is just division, but the numbers are not quite as nice as they were the first time. 99 still won't go into 25. I'm still going to add a decimal. I'm still going to add a 0. But when I put on this 0, I get some very unfriendly numbers. For me, I like to think of this 99 as being almost 100. And I like to ask myself, how many times would 100 go into 250? Well, it's going to go in twice. 2 times 99 is 198. I get a remainder of 52. Notice this is not a repeat. Add a 0, bring it down. 99 goes into 520 how many times? Well, 100 would go into 520 5 times. Let's try that. 5 times 99 is 495. You're left with 25. Hey, that's what we started with. Let's see what happens if we go again. How many times does 99 go into 250? Well, I already did that. It went in twice. It's 198. Take a look. You end up with 52. 25, 52, 25, 52. You've got yourself into a repeating pattern. I'll bet if I were to do another 0 and bring it down, I'm still at 520. 99 goes into 520 5 more times, and I'm going to end up with minus 495. Wow, that's really bad. Leaving me with 25 again. Notice this time it's not just one number repeating. It's not a non-repeating followed by a repeat, but instead you've got two numbers that keep repeating forever. 25, 25, 25, 25. And so I would write this as 25/99 is 0.25 with both the 2 and the 5 repeating forever. See how that works? Now, if this had been a mixed number like 3 and 25/99, just like on the other slide, I would just go through and add the 3 back in and end up with 3.25. We're really only concerned with fractional parts right here. There's a lot of different things that could happen, but it's important for us to realize that fractions or rational numbers written as fractions will always turn out as either being whole numbers or integers, decimals that terminate, or decimals that repeat. That's rational numbers. I hope this has been helpful to you. As always, thank you so much for joining us here today. Make sure you smash that like button for me. Turn on your notifications and hit the subscribe button so that you can follow along with all the pre-algebra that we're doing this year. We do wish that you would keep coming back and join us. If you get an opportunity, check out our algebra information as well. That would be the class that comes after this course. So when you finish this, make sure you go back and cycle through that as well. Leave us a comment in the comment section letting us know that you're watching. Leave us some suggestions for how to improve, or if you're just enjoying what's going on, make sure you're letting us know how this is helping you in your classroom. As always, we wish you guys the very, very best of luck. Best wishes. Take care. Bye-bye.